Hi, myself Hardik Pandya, and I am a professor in Department of Electronic Systems Engineering at Indian Institute of Science, Bangalore. So, as a part of this particular course on neural science for engineers, I thought of taking two kind of a TA class so that the engineers who are taking this particular course would understand how the fabrication or the process for fabricating several micro devices can be used to understand neural signals, right. Now, we have already seen through the course instructor Dr. Vikas, who is also a neurosurgeon, that how the kind of brain works, right, and what is the anatomy. We have also seen some of the signals and how the processes are made. Now, in this work, what I want to show it to you is that what kind of different neural signal acquisition approaches are there, right. So, you already know about ECG, right. What is ECG? ECG stands for electrocardiogram, but when you talk about EMG, it stands for electromyogram. So, ECG are basically the signals that are originating from the heart muscles, right. So, it is ECG that we generally see in our daily basis in movies or in your serials, right. There is a ECG, echocardiogram. Then there is a EMG, like I said, it's a muscle movement. So, if I move my muscles, right, if I put an electrode, you will see a potential generating from the muscles. But when it comes to brain in particular, then we look at several things. One is your EEG and second is MEG. So, generally you will see the term EEG, which stands for electroencephalogram, but that is outside. That means when we take the signals from the scalp, right, then you get the EEG. So, and the voltage value, the amplitude, right, that you find in the EEG signal is way lower than the amplitude of ECG or EMG. ECG and EMG, the voltage range is of millivolts. EEG, the voltage range is of microvolts. So, that is where the difference is, but the first question that will arise is why EEG is having lower voltage or lower potential than ECG and EMG. And the reason is that the impedance provided by the skull, right, would reduce the signals that is originating from the brain. Also not only that is only one of the reason, but also the muscle movement, right, the muscle movement of our heart and of our muscles, right. So, that is way higher compared to that of brain. So, the signals originating in the brain is of lower potential. Now, I am putting in very easy terms for you to understand, right, not really into the bookish term, so that we understand how to measure those signals and what kind of different devices that we can fabricate. So, we can divide the approaches for brain computer interface, right, which is BCI, into two particular modalities. One is a non-invasive technique to measure this EEG signal or the signals arising from brain, EEG or MEG. That means that non-invasive is without invading, right. So, you may have seen the terms invasive, right. Open heart surgery is invasive. Minimally invasive, blood glucose monitor, minimally invasive. Urine, through urine we test different pregnancy tester, right. So, it's a minimally invasive. It's not actually minimally invasive because there you are not invading something, but blood glucose for sure because you are putting a needle, right. When it comes to invasive, that means you are actually invading, means you are going inside. For example, if you open the skull and understanding the signal from the brain or acquire signal from the brain, then it becomes invasive. Third thing is, so one is non-invasive without invading. It can be your breath analyzers, right, that you just have to measure the signatures of the breath, or EEG measurement like 1020 system you may have seen. And when it comes to minimally invasive, I give an example of a blood glucose monitor, When it comes to invasive, right, then there are several different techniques. In this particular course, let us keep ourselves limited to ECOG, SEEG and intracortical implants. Now again, to make it simpler, when we take the signals directly from the brain, it is electrocardiography. Okay. So when you see this one, this particular image, right, that we have taken from 30th Canadian Conference on Electrical and Computer Engineering, and also we have taken another paper from Frontiers in System Neuroscience, which we have acknowledged on this slide. What we see here is that how the EEG electrode placements are done. Now you can see very clearly in this particular slide. I will just put a laser pointer. In this one, what we see is there is a 10-20 system, right. This is a 10-20 system. Based on that, where to put the electrodes and how to measure the or how to acquire the signals. A simplified way, this F stands for frontal, frontal is front, T stands for temporal, temporal, C stands for central and O stands for occipital. Alright, easy. Frontal F, central C, occipital O, temporal T. Alright, this much easy. Now if I place the electrodes in this given fashion, what will happen is that we can get these EEG signals, and that EEG signals that we record has lot of application also to understand in several domains. Let me take an example of seizure. Seizure is epilepsy. So if somebody wants to understand whether the epilepsy is focal to a certain point, let's say it is just on CZ or C4, or it is a generalized epilepsy where it is in most of the electrodes, or it is focal to generalized, that means it started at some point and then it spreaded over different electrodes, then one can easily understand. Alright. Now when we talk about the ECOG, that is electrocardiography, as I said, it is a signal, again a brain, originating from the brain, but we are directly placing the electrodes or a flexible implantable chip onto the brain, Now, so for that we need to open a skull. Of course, when I say we, is not you and me, is neurosurgeon like Dr. Vikas, right. So you can he can open a skull, or a neurosurgeon can open a skull. Then there is a dura, you can open a dura, and then there is a brain, right. And in the CSF, when you place a device on this particular brain and you measure a signal, we know whether it is sensory area we are measuring or it is a motor area where we are measuring, right. And that particular data that we get is called ECOG. Alright, and then there is a SEEG illustration which is over here, right. But the point is, let us restrict ourselves to ECOG and EEG. So I hope that in this, from these two slides, what we understood is what is the difference between this EEG signal, which is electroencephalogram, versus electrocardiography, right. Now let us go to the next slide. Okay. So from non-invasive to invasive neuropotential acquisition. So like you see here, when we go from EEG, which is non-invasive, to IEEG to SEEG, actually the changes happens. Particularly what we have to understand is that what exactly happens when we go from non-invasive to invasive. First and foremost is that the biopotential amplitude would increase, the biopotential frequency would increase, signal to noise ratio would increase, right. And that's good because now directly we are touching the brain, right. Then field of view is it decreases, right. Of course, because we don't depending on what kind of craniotomy surgeon operates, right, the area would change. The spatial resolution increases, invasivity and complexity increases, because now we are opening the most delicate and kind of unknown region of the human body, right. Still lot of research is going on in the area of brain, right. So invasivity and complexity increases. Influence of anesthetics, right, also plays a role, because when you want to go for that kind of surgery, you have to anesthetize the patient. Influence of narcotic, analgesic also increases. There is a chance of tissue damage, and that's why when we use implants, we also go for something called toxicity studies, right. So if you use the implant, and depending on what kind of material that you use in the implant, is it a biocompatible material? If it's a biocompatible material, what is the material made up of? And if and once you implant that device into the brain, then what kind of toxicity effect it may have, right. So all these things one has to see when we move from non-invasive to invasive neuropotential acquisition. Next is, let us understand why we want to go for invasive EEG or IEEG, right. So brain functionality mapping. Now we need to know what kind of signals are originating from different regions of the brain, and from that we can map the brain. It's an extraoperative or epilepsy surgery evaluation. Sometimes the drugs, so when there is epilepsy, it's also called seizures. A person has to generally is advised or administered different kind of drugs that are called anti-epileptic drugs, but there is one single kind of epilepsy which is called in which the surgeon has to operate the patient, all right. So for that one we need to understand or check the sensory outcomes during surgery. We need to understand whether it can be used with direct cortical electrical stimulation, and we can also understand brain tissue properties. So that means that if I want to use the same kind of device or a deep brain stimulation electrode for treating Parkinson, right, what kind of signals are requiring, where to implant this electrode, how long the electrode should be implanted, whether you implant the electrode, what kind of toxicity effect will be there, whether there will be any tissue damage, right. So all these things one can understand when we go for IEEG or invasive EEG. But if there is a advantage, then there are certain limitations, and the limitations of electrocardiography or IEEG are limited recording time. Second is limited area of consideration. Third is risk of damaging tissue. Next is CSG leakage, right. Next one is intracranial bleeding, and final is infection. So what we are focused on is that as an engineer, and if you know as a process designer for designing different microchips or implantable flexible micro devices, can you design a microelectrode array, and if you are designing that one, then can you record those signals arising from the brain post neurosurgery? But also when you implant this electrode, what kind of signals are originating, can you acquire those? Now the question is, like, if we want to go into this particular research domain, first question would always be why, right. Why we need to do this? Are there already existing products what we are talking about, right, and what forces us or compels us to go in that particular direction of fabricating our own devices, all right. So if you understand the commercially available electrodes, then it costs about $5,000 for one A4X4 TET 5mm 150, 200, 121 with connectors and electronic only from Neuronics Incorporation. This one, it is costing how much? $5,000, right. Now if you go for a B, which is this one, it will cost some $700, right. Then if you go for the C one, right, with this one, it is from Themos Recording. There is a track neural recording array, right. Then there is a NeuroPixels probes are being distributed by IMEC, right, like NeuroPixels probes are here. So the point is that, are we ready to invest this amount of money to study different brain signals? And now there are multiple questions. Yes, we can, if it is useful and it is affordable. Second is, how many of these devices you can procure, right. This procurement of these devices, that means we are loading the import, right. How to reduce the import, how to improve the export, right. So can we fabricate these devices here in our country? If that is the first question. If yes, then what are the process flow to fabricate it, right? That is the second question. And what will be the affordability point of view or margin that we can bring it, that is the third point. Fourth point is whether those electrodes will work or have the similar efficiency like the existing commercially available devices. Fifth point, can we acquire those signals and record it with the existing electronics that it's available commercially, right? So there are several things that one has to take care of it. How many devices you can fabricate, right? And what kind of fabrication process are there. So taking all this into consideration, we can think about what are the process flows and what can we do from the microengineering fabrication process point of view. The second thing that is of interest is of micro electrode array, and this electrode array are on the surface of the brain, right. See, the one that you are looking at are kind of a needle, what we call is a micro needles, or some people call is a probe, right. So this needle can be implanted deep inside the brain, it goes deep inside the brain, right. But when you want to know the surface, what kind of signals are originating from the surface of the brain, then there are several ways to fabricate flexible electrode microelectrode array. And from the literature, what we found is that on the left side what you see is a bioresorbable ECOG electrode array. There is external connections, and then there is a highly doped silicon nanomaterials. We use nanoporous silicon also, and then you can also see that this is a bioresorbable. What do you mean by bioresorbable versus biocompatible? Biocompatible is that the device is compatible with the human body, right, or a animal body, right, depending on whether we are using on a rodent model or on monkeys or on humans, right. So that is biocompatible. Second is bioresorbable. Resorbable means it will dissolve in the brain, it will dissolve inside the body, right. So once you implant it, you don't have to do the you need not to take it out again, because it will dissolve, right. There is an advantage of using bioresorbable over biocompatible. Of course, bioresorbable is also biocompatible, because otherwise it will form the toxins. So this example that you can see here, there is a silicon dioxide which acts as an insulating material, that is a silicon, there is a PLGA material, this is a degradable substrate, and this exposed silicon electrodes over SiO2 encapsulation layer. We have schematic of exploded view, which is right over here, and then you have photographs of bioresorbable electrodes with 4 channels, which you can see here, right. Then you can see in this particular thing, so since there are 4 different channels and you have different electrodes, you can also measure that what kind of ECOG signals are arising. Now why I am not talking about ECOG and not EEG, because you are implanting this electrode onto the brain of the rodent model or on the rat's brain, and you are measuring electrical signals. Now you can see that in the right side, the sleep spindle activity is about 50 microvolts or 100 microvolts, right. Cortical electrode, control electrode and bioresorbable electrode. So you have the difference of 50 microvolts, but at the same time, if you create an epilepsy by using epileptic inducing drugs, then you can see there is a intralacteal spiking activity, and the range here suddenly becomes 1 millivolts. So the range changes from few microvolts to 1 millivolts, that means there is a seizure, right. Same thing if you see this is spiking activity, okay, then this is a seizures, right. So you see the seizures clearly you can see in this bioresorbable electrode versus a control electrode, and the seizures are also of very high amplitude, right. The next one is there is a theta oscillation, as you can see here, and then there is a fast spindle oscillations, as you can see here. The point that I am making is that using this flexible bioresorbable 4 channel electrode array placed on the cortical surface of the left hemisphere of the rat, the authors were able to, like June et al. Or UK June et al. Which is this work is published in Nature Materials in 2016. They were able to understand what kind of electrical signals they can measure using a bioresorbable electrode, and how the performance of bioresorbable electrode is different compared to the control electrodes. Also, to understand whether the electrodes, what kind of activity, whether it can pick up the activity like interactive spiking activity or seizure like spiking activity, they did further experiments and they were able to measure it. Now This is about the microelectrode array literature. That was the first paper. The second paper that I am showing it to you is by Z and Kijun et al. And it is published in Scientific Reports in 2017. And here what they have done is they have again fabricated ECOG electrodes on a flexible substrate, and then there are 3 holes in this one to load the drug right when the chip is implanted onto the animal brain. And you can see the flexible electrodes array, cross sectional view of a microelectrode, which is right over here, which is this one. And then you can see the bottom material, right, the substrate is PI, which is flexible in nature. Then you have your chrome, you have your AG, and you have your AU. Finally, gold is used to acquire the signals or record the signals. ECOG electrodes device with 32 microelectrodes, as you can see the numbering from here. So last paper, right, what we saw is about 4 electrodes. Here there are 32 electrodes. Also a microscopic image of the microelectrode and 3 large holes for drug injection. So you can inject different drugs using these 3 holes right when the device is implanted onto the rat's brain. Finally, you can see the actual photograph of the fabricated device. So what we see in this particular case is that when there is a normal signals, ECOG signals which are normal, you can see this amplitude range, and it is a voltage in microvolts. And when it is epileptic rat, that means when we can create epilepsy, then you can clearly see the spiking activity, right, and the amplitude increases many folds compared to the normal ECOG signals. Next one is the red area has a highest amplitude, so they have also mapped it, and then they have done the analysis to understand that which area shows the maximum amplitude and most active under epilepsy, which allows to identify epilepsy lesion in the brain. So when you create an epilepsy, if it's a focal epilepsy or a certain epilepsy generating only in the certain area, we can easily understand using this kind of flexible device. Now the next one here is the flexible electrode array placed on left hemisphere of the brain, zoomed in photo of the microelectrodes, and ECOG are normal in the, so this is again a normal and when there is a epileptic conditions. So the point of showing you all this particular literature is to make you understand that there is a possibility for people who understand fabrication process, microfabrication process, to fabricate this kind of devices. It's not too difficult. Once you understand, it becomes very easy, right? But to understand how we can deposit the different material, whether it is a metal or whether it is an insulator or whether it is semiconductor, we need to understand something called PVD. PVD stands for physical vapor deposition. All right, so you can see here, right, in this particular slide, thin film deposition, which is PVD. We have thermal evaporation, in which you can see that there is a boat, then E-beam evaporation, and then there is a sputtering. But let us start with thermal evaporation. So thermal evaporation, as its name suggests, right, as its name suggests, we are heating a material which is kept on a source. You can see here there is a source holder, right. So there is a source holder on which the material is kept, which is blue in color, and then when we heat this source holder, which is also called boat, BOAT, boat. When you heat it by apply, now when you have a boat, that means our source holder, right, it is made up of a metal. So if you apply a voltage, what will happen? Because of the resistance of the metal, the current will flow, and there is a generation of I square R heating, which will heat or melt the material loaded onto the boat, onto the source holder. And because of the melting of the source material, it will start evaporating. That evaporation is caused by we have thermally evaporated the material. That's why the name comes as a thermal evaporation. Now what are on the top? This one, right? This is a substrate holder which holds several substrates, and this is a rotating holder. Rotation is to make sure that the uniformity of the deposited film is intact. And finally there is a vacuum chamber or vacuum vessel. So what will happen is that at a single time you can deposit different materials, not different materials, one after other materials, but the same material you can deposit on several wafers in a single time, and that is the advantage of using this thermal evaporation. What is the disadvantage? The disadvantage is that when the source material has a higher melting point compared to the source holder, here they call furnace, but the right term that, or most of the papers or the books that you will find, they write this as a boat or a source holder, right, and this as a substrate holder. the top one is a substrate holder, the bottom one is a source holder. So, when the melting point of the source, that is the material that we want to deposit, is way higher than the melting point of the source holder, then we cannot use thermal evaporation, and then in that case we need to move to the electron beam evaporation. Now, why to use this vacuum, right? So, this is also called vacuum based evaporation, okay, vacuum evaporation. So, the reason of using vacuum is to improve the mean free path. Now, what is mean free path? The path before which these atoms will start colliding with each other. So, how long this can travel without colliding with each other, right? That is a mean free path. Higher the mean free path, right, better it is for us for getting the depositor film. Also, like I said, rotating the film, rotating the holder will improve the uniformity of the film. But in the case where your source is having very high melting point compared to source holder, we go to second system, which is called electron beam evaporation. Alright. In electron beam evaporation, you have a crucible which you can see here, then you have electron gun which you can see here, and when you apply and then electron beam comes and it can be incident onto this crucible where the source is loaded. So, when the source is loaded and the electron gun comes and it is incident on the crucible, this will start melting, it will start melting, and when it start melting it will evaporate, and when it evaporates it again gets deposited onto the substrate. This substrate is attached to the substrate holder. Now, here the crucible, we are not heating the crucible, right. Crucible is a material which is made up of material which has a very high melting point compared to any source that is used inside the e-beam evaporation. So, for example, graphite, right, that is one of the material that one can use for crucible. The idea is that using electron beam you heat or melt the source, and the crucible we are not heating, that is why this is a electron beam evaporation. You are using electron beam to melt the source material which is loaded onto the crucible, which is a source holder, and this material will evaporate and it will get deposited on the source, on the substrate, and the substrate is attached to the substrate holder. Next, when we go, so again this is using the vacuum, right. So, vacuum is used for increasing the mean free path, remember, okay. The next one is the sputtering unit. Sputtering unit, in this one we are not actually melting it, we are not melting the source material, but what we do is we dislodge the atoms. We use argon and neutralize atom, we use argon to heat this cathode, and the anode is where the substrate is there. Now, when we heat this cathode with argon, right, in presence of plasma, what happens is that the atoms from this target material will get dislodged, and when it gets dislodged it will start moving towards the substrate, right. You can see this one in this particular direction, and when it starts moving towards the substrate, it will start depositing on the substrate. This deposition, if you have seen how the raindrops when there is a rain and raindrops falls on the roof which is made up of metal, you will hear a sound, and that sound is similar to the sputter sound, alright. The raindrop falling on the metal roof, if you hear it carefully, that is how the sputtering works. So, the sputtering names comes from sputter, and sputter is similar to raindrops. In this case there are no raindrops, we are talking about the dislodging the atoms from the cathode or from the target, and this will move towards the anode on which there is a substrate and the deposition occurs. So, this is a mechanical way of depositing a film. The thermal evaporation and e-beam evaporation is we are heating it, we are using electrical energy, right, to heat the material, whether it or electron beam. In this case we are mechanically dislodging the atoms, right. Now, this is called physical vapor deposition because we are physically evaporating the material and we are creating into vapor and depositing it onto the substrate. But there is a chemical vapor deposition, and chemical vapor deposition, as you can see on this particular slide which is right over here, right. What happens is that you create a chemistry where the chemical or the gases that forms this particular layer, right, can be passed through the chamber, and those gas will react with the substrate which is we called as a diffusion of precursors. It goes inside and it reacts, which is either it is absorption or desorption, and then that reaction occurs, which is we call as a chemical reaction. Then there is a desorption, and then there is a diffusion, so of byproducts. So whatever the byproducts are that will come out of the chamber. Here we are using chemical as a medium to create the film. That's why we call it a chemical vapor deposition, right. So silane is used and several other materials are used to create different kind of films. So again, if I repeat it, then we have a diffusion of precursors, then it goes as an adsorption on the surface of the substrate, then there is a chemical reaction, it forms a film, it's certain material will get dissolved, and finally the byproducts will come out of the chamber. This is known as chemical vapor deposition. Again, I am talking from a very peripheral point of view so that you don't get confused. Okay. Now, so in general what we understand is PVD versus CVD, but in CVD there are several types. Like in PVD there are 3 types: thermal evaporation, E-beam evaporation and sputtering. In CVD also we have several types. One is a low pressure CVD, second is atmospheric pressure CVD, and then there is a continuous gas is supplied where you have LPCVD, then you have PECVD, and then you have MOCVD, then you have atomic layer CVD, which is ALD, then you have thermal ALD, then you have atmospheric pressure CVD, which is APCVD, you have low pressure CVD, LPCVD, you have plasma NN CVD, PECVD and so on, right. So several types of CVD. So as you have noted, right, that physical evaporation is more versatile method than CVD, since it allows to deposit almost all the materials in fabrication. But at the same time, PVD has a limitation that we cannot get a good surface coverage and step coverage in particular. So as you can see, the shadowing effect causes the step coverage to be poor in PVD. Now in this module, let us understand PVD and CVD little bit more in detail. So in the left side, what you can see is a E-beam evaporation system, this particular one. In the right side you can see thermal evaporation system, which is right over here. This is also a thermal evaporation system. Okay. So physical methods produce the atoms that deposit on the substrate. It is evaporation or sputtering. Sometimes it is also called vacuum deposition because the process is usually done in an evacuated chamber. So generally the PVD is used for depositing metals, and dielectrics can be deposited by specialized equipment. The evaporation techniques of PVD, we use a vacuum chamber. I told you to improve the mean free path, and generally the vacuum is pumped down to less than 10 to the power minus 5 torr. The heater can be of resistive type. Generally tungsten filament is used and it heats up and current flows through it. But more popular is an electron beam evaporation, as I told you, because where the material that you are using, if it has high melting point, it cannot be evaporated using thermal evaporation, but we can use the E-beam evaporation. Again, depending on the type of the evaporation and the material that you want to evaporate, you can either categorize it as a thermal evaporation and evaporation and take that particular technique to deposit the material. This is again a similar thing in a different form. A very dear friend of mine, he has given me this image. This is a source holder. You can hold different boats into this, boats or a source holder, right, and whenever it connects with this particular electrode, it starts heating because the power is given to this particular source holder. Then you can rotate this and you can connect this one, then you can again rotate, you can connect this one. So you can deposit 4 different materials inside the vacuum chamber. This is a vacuum system, there is a source material or a heater, there is a wafer holder with wafers, and the thermal evaporation, as we have discussed earlier, relies on thermal energy supplied to the crucible or a boat, right, to evaporate atoms. Evaporated atoms travel through evacuated chamber and reaches to the substrate. Surface reaction occurs very rapidly, and that's why there is a very little time of rearranging the surface atoms after sticking, and that's why when we see the deposited film, generally it is amorphous in nature. you may know what is amorphous, what is polycrystalline, and what is single crystal. So sometimes when we know, we need to know. So the question is how we will know whether the film is amorphous or film is polycrystalline. Why this is very important? Because certain times you need to fabricate devices like piezoelectric device. Now what is piezoelectric? Piezoelectric is a material or is a property where you apply a pressure, there is change in voltage, and vice versa. When you apply a potential, there is a change in the pressure. So for those kind of material, for example, if we use PZT, lead, zinc, titanate, then we need to know that the crystals are oriented in a certain fashion. And also polycrystalline film shows a better sensitivity if you go for a gas sensors and some of the other sensors. But when we go for thermal evaporation, since there is a very little time of rearranging of atoms, the most of the time the film that we got is amorphous in nature. How to get a polycrystalline film? So there are two ways. One is that you can heat the film during the deposition. That means that if your wafer holder or a substrate holder has a heater, right? We have seen earlier that there was a heater indicated onto the substrate holder. Then the rearrangement of the atoms can be made better. Second is that if you take out the film, you can deposited film, you take it out and you anneal it in a chamber, right? You heat it in a chamber, then you can again see that it has a polycrystalline nature. How you can measure whether it is polycrystalline or amorphous? Using a technique called X-ray diffractogram, right? That is a material characterization technique. So thickness, uniformity and shadowing by surface topography and step coverages are the issues. So one can go for E-beam evaporation. Again there is a photograph of this E-beam evaporation. There is a schematic here and you can see there is a crucible, then there is a source and there is molten source. Molten source is because there is a filament here and the filament will generate a electron which will pass through the accelerator electrode. It will bend because of the deflecting magnet and you can incident those electrons on a given surface. So E-beam evaporation is a physical deposition technique because here we are physically evaporating the material and depositing onto a substrate, and that allows the user to evaporate materials that are difficult or even impossible to process using standard resistive thermal evaporation. Some of these materials include high temperature materials and some ceramics. So to generate the E-beam, an electrical current is applied to the filament which is applied over here, right? And electrical and then which is subjected to a accelerating electrode. This accelerating electrode with helps to accelerate the electrons further and to escape the filament. The electrons are then focused by the magnets to form a beam. You can see here on the laser pointer, right, directed towards the crucible that contains the material. This is a crucible with the material. The energy of E-beam is transferred to the material and the material will melt and will start evaporating. Many materials will either melt or evaporate or sublimate depending on the material property. So what is the, so this is actually let me go back. So this is the E-beam evaporator. This is a shutter, right? So until the material is properly melt, we don't open it. And then how to measure it? So there is a QCM which is called quartz crystal monitor. It is used to measure the thickness of the material. So when you start evaporating the material, you don't open this shutter. Above the shutter there is a substrate holder. Somewhere here the substrate holder will be there. This is a shutter, right? It will shut off the deposition. So it will not allow the material to get deposited onto the substrate until we remove the shutter from the path from which the atoms are evaporating and depositing onto the substrate holder. So somewhere in this chamber there is a quartz crystal monitor. This quartz crystal monitor, as you know, quartz is a piezoelectric. It is used to measure the thickness of the film. So when we get the right thickness, right rate of deposition rather than thickness, we can open this shutter and start and allow the material to get deposited onto the substrate holder. So the role of shutter is to shut off this particular deposition until we get the rate of deposition that we desire. Now if I go to the next, so and then there are different kind of source holder. I'll talk about it later. So here you can see that this QCM, which is also called a deposition monitor or quartz crystal monitor, as I said, it is there to understand what is the rate of deposition. Then there is a hearth, there is an electron gun and the electrical supply, and there is a water cooling. Why water cooling is given in the back? Because to reduce the heat effect that happens because of the electron beam incident onto the substrate onto the source holder. The source holder is a graphite material, but we need to keep it at a lower temperature by using water cooler. So water cooled crucibles are used in deposition and or in the depression of the water cooled copper hearth, right. It is a water cooled copper hearth, and the back side the water will come, which will help it to maintain the temperature or not rise temperature beyond certain value. So the electron beams are thermo-ionically emitted from heated filaments, but are shielded from direct line of sight, right, the evaporant charge and the substrate. The filament, which is a cathode assembly point, is biased negatively with respect to nearby grounded anode. And finally, a transverse magnetic field is applied, which serves to deflect the electron beam in 270-degree circular arc, and it focuses onto the earth and evaporant charge at ground potential. So this is a video. Let me see if I can play it. If not, yeah, just quickly see how the electron beam evaporator works. It is from Georgia Tech, Microengineering Research. So I hope you have seen the video, right. Now we will talk about e-beam evaporation, in which we practically, what is the power that is used, right? What power density is? The power density is about 10 kilowatt per centimeter square. It can, but for dielectrics it requires 1 to 2 kilovolt per centimeter square. So contamination level of the deposit film using e-beam is less than other PVD methods. That's the advantage. Also the electron density Je leaving the hot filament is due to thermoionic emission. We know that, and that if somebody wants to calculate, then they can calculate using Richardson equation, which is given over here. And near to evaporant substrate surface, evaporant flux shows a laminar flow, and uniformity of thickness can be described by cosine law. So you will know that where is the substrate holder. Substrate holder, if you have seen, is perpendicular to the source material, and the reason of having it at a certain degree is when you understand the cosine law, you will understand it better. Now when we talk about the e-beam evaporation, we also have to understand that what kind of different evaporation sources are there. So one is a single pocket source, as you can see on the left side here. Then there is a rotary pocket, which is over here, and finally there is a linear pocket. In single pocket, as the name suggests, you can only have one particular source material. In rotary pocket, you can have 4 to 5 different rotary source material, because you can see one which is exposed here, second would be here, third would be here, and fourth will be here. So suppose you want to deposit chrome, and then after chrome you want to deposit gold, you can use this chrome, deposit it, then turn it, so the gold the substrate, the source holder that will have gold will come into this particular region, and then we can again deposit gold using e-beam evaporation. Then there are linear pockets. That means that on 4 pockets, whatever the area, whatever the material you want to deposit, you have to bring that particular source holder where you can incident the electron beam. So linear pocket e-beam is similar to a rotary pocket source, except that the pockets are arranged in a line and are indexed into a position in a linear fashion. A rotary pocket has all the same parts as a single pocket, like here, right, except that the water cooled copper block is essentially a turret of multiple pockets, right. You know turret means, if you have seen or used microscope, there are different lenses, right. So you can change the lenses. That holder is called turret. So is essentially a turret of multiple pockets. With this design, a number of different materials can be evaporated sequentially from a common magnet, emitter or sweep coil. Obviously this design includes additional shielding to prevent cross contamination. The pocket in position is chosen via a motorized rotary indexer, right. So generally when we go for e-beam, you will see that most of the e-beam will have the rotary pocket because of the given advantages right over here. Here if you talk about single pocket, a water cooled copper block is bored out to have a pocket in the shape of an inverted truncated cone, which you can see here, and in this we can place the source material. Source material is placed within this pocket or within a crucible whose exterior fits squarely with the pocket. The crucible has a smaller similar pocket within it, so you can load the crucible, and then in the crucible you can put this source, right, not directly in the pocket. So don't understand differently. You have a crucible which you have loaded into the pocket, in which there is a source material. Before we go to sputtering, let us understand that the thermal evaporation we have seen has 2 different types. The PVD technique that we have used has 2 different types. One is thermal evaporation. evaporation, and second is the electron beam evaporation. We have seen how thermal evaporation works, we have seen how e-beam evaporation works, we have seen CVD techniques, and all these things are useful for us to fabricate the devices that we have seen earlier, right. So, with that I will stop the module here, and we will see what is the way to deposit sputtering, what kind of different techniques are used to sputter, what kind of different sputtering techniques are there. So, one is the PVD technique, there are 3: thermal, e-beam and sputtering, but within sputtering there are further subdivision. So, we need to see how those works. The idea of showing you this particular module is to make you understand that the material that one uses for designing this micro needle or surface microelectrode array, right, like gold or silicon dioxide, right, we can use this PVD technique. The idea of showing you CVD is that we can deposit insulating material like silicon dioxide. Now you understand that if I have a material already deposited onto a substrate and the melting point of that material is below the melting point of silicon dioxide that gets deposited, right, then it cannot work. And that is why we will talk about a technique called PECVD, plasma enhanced chemical vapor deposition, which is used to shield the metal at and deposit this silicon dioxide at a lower temperature. Lower temperatures can be 100 and 200 degrees centigrade, which will not affect the metal below it, that is gold will not get affected. But LPCVD goes for very high temperature, about 900 degrees centigrade. So, we cannot use LPCVD, we have to go for PECVD. Now, I am bringing all this thing into your understanding or knowledge, so that we can see that when we fabricate a device, a process flow, I will show it to you, how different methods that we are learning here can be utilized to fabricate those devices, right. So, with that, let us complete this class. I hope you understand a bit on PVD techniques, a bit on CVD techniques, a bit on microelectrode array and a bit on micro needles. We will see how we can fabricate those things in the next class. Till then, take care, bye for now.